Today I am going to discuss how we find particular integral in the general solution of a linear homogeneous differential equation, linear non-homogeneous differential equation with constant coefficients. That is, we consider an equation d square y by dx square plus a1 dy by dx plus a2y equal to a0 of x. This is a linear non-homogeneous differential equation with the constant coefficients. Okay, so we know that the general solution always have the two parts, complementary function and particular integral. We already discussed the method of finding complementary function. So here we discuss how we find particular integral by method of variation of parameters. And for that we should know the linear independent solutions of its homogeneous part. That is, initially we assume that y1 y2 are the two linearly independent solutions of d square y by dx square plus a1 dy by dx plus a2y equal to 0. Okay, if y1 and y2 are two linearly independent solutions of the homogeneous part of the given differential equation, you can assume the particular integral as u y1 plus v y2, where u and v are functions of x. Okay, u y1 plus v y2, and we can find out u and v using these expressions, where u equal to minus integral y2 into a0 of x divided by w, where w is the Wronskian of y1 and y2, and v is integral y1 into a0 of x divided by w, where w is the Wronskian of y1 and y2. And we will go through an example where we can find out this particular integral by method of variation of parameter, and this is an example. Okay, the problem is, solve the differential equation d square y by dx square minus 2 dy by dx plus y equal to e raised to x into sin x. So that's the question. The equation becomes d square minus 2d plus 1 of y equal to e raised to x into sin x. Okay, so in this case the complementary function is c1 e raised to x plus c2 x e raised to x, as the independent solutions are x and x e raised to x. This generally we find out by solving the auxiliary equation and identifying the roots. Anyway, initially we should note that e raised to x and x e raised to x are the independent solutions for the homogeneous part of the given differential equation. Okay, now by method of variation of parameters, we assume that particular integral is u into e raised to x plus v into x e raised to x, as e raised to x and x e raised to x as independent solutions of the homogeneous part of the differential equation. Okay, so here u equal to minus integral y2 into a0 of x by w with respect to x, and v equal to integral of y1 into a0 of x by w with respect to x. First we find Wronskian of e raised to x and x e raised to x, that is determinant y1 y2 y1 dash y2 dash. Okay, anyway, Wronskian of y1 y2 can be determined, and we will get that it is e raised to 2x. Okay, now apply the formula for u. You will get u equal to minus integral x e raised to x, that is our y2, e raised to x into sin x, that is our a0 of x, divided by e raised to 2x, that is our w. Okay, so we integrate that function with respect to x. You will get u equal to minus integral x sin x after cancelling out that e raised to 2x. We apply integration by parts, so that we get minus first function x into integral of sin x, that is minus cos x, so x into minus cos x minus integral of derivative first, that is 1, then integral of second minus cos x, integral of minus cos x, that can be written as minus of x cos x plus sin x, which is x cos x minus sin x. So we get u. Okay, then v equal to, similarly applying this formula, we get integral e raised to x into e raised to x sin x divided by e raised to 2x. Here again e raised to x get cancelled, we get integral of sin x, that is minus cos x. So the particular integral becomes, this is expression for the particular integral, that is u e raised to x plus v x e raised to x. Substituting for u and v, we get the particular integral is e raised to x into x cos x minus sin x minus x e raised to x cos x. So the general solution is y equal to complementary function plus particular integral. So this method of applying this method variation parameters for finding particular integral.